Okay, let's look again at the pendulum that we introduced in the beginning part of this segment. And this time we're going to add damping. You explored the properties of damping in the exercises for the beginning of this unit. And you'll recall that whereas without damping, we had the whatever total energy we started with, we continued, the orbits continued on that same total energy shell. And so here's where she's showing you in this animation, he's showing you that if you start close to the top with just a little bit too much energy, you'll keep spinning around the top forever. And he's showing you the phase portrait on the right in the phase plane, and he's reminding you that there are, if you take the second order scalar ODE point of view, there are two scalar trajectories. There's the position trajectory and there's the velocity trajectory. That was previously. And you'll notice that intuitively it's clear that if you started the pendulum at the very, 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 very top, where it was standing straight up, then that's a fixed point. And I think it's clear from this little animation, even if it wasn't clear to you intuitively, it's clear that if you perturb the top fixed point just a little bit, you'll get instability. You'll never have the pendulum return to that top position. Well, will the unstable fixed point become stable, or will it stay unstable when we add damping? Those are the kinds of questions that are going to be urgently important for us when we're trying to stabilize our gates in locomotion. So it's pretty easy for you to see intuitively that the damping is going to stabilize the body. If you think the bottom equilibrium point, if you start the pendulum just at the bottom and you put some damping in there and you perturb it away from the bottom, you know what it's going to do. It's going to swing down slowly and lose its energy and end up at the bottom state. What about at the top state? Is the top fixed point still unstable, or is it somehow stabilized by the damping? Okay, let's look at the vector field expression for the damped pendulum, which we introduced at the end of the previous unit. And let's remember one of the exercises that you worked on associated with this unit, where we asked you to compute the power for the damped pendulum by taking the total energy formula for the pendulum, taking its gradient, and taking the inner product of that gradient with the vector field of the damped pendulum as expressed in equation 1. Remember why you take that inner product. It's because you take d by dt of the total energy and express that as a function of state in order to get the power formula. And when you computed the power formula, I hope you'll remember, or you'll go back and check to see that you got this non-positive expression, which is exactly the way it should be, because what it tells us in equation 2 is that the damper, the coefficient B is the coefficient of the damping, or the viscous damping of this pendular system. It's the damping that's sucking the power out of the total energy of the pendulum at this power rate. Okay, let's interpret for nonlinear systems the property of having multiple fixed points. Remember, for a linear time invariant system, such as the damped harmonic oscillator, we can't have multiple fixed points. Well, if the matrix representation of the vector field is non-singular, then the only fixed point would be at the origin. In contrast, for the pendulum, we know intuitively that we've got two different fixed points. We've got a fixed point at the bottom, and we've got a fixed point at the top. And here I'm showing you on this picture, I'm reminding you in the phase plane that when you're at the bottom, namely when the angle is 0 and the angular velocity is 0, clearly you're going to stay put, you're at a fixed point. Whereas if you're at the top, if your angle is at 2 pi away, or negative 2 pi away, and your velocity is 0, and you're exactly pointing up, then you'll stay put. But if you deviate in the slightest bit from this fixed point, you're going to be swinging around the fixed point forever. You're going to be orbiting around and around and around, which is what that orbit is showing you. Okay? Or if your energy was just a little bit less and you're close to the fixed point but just not quite there, then you'll be orbiting back and forth, which is what this trajectory looks like physically, and you'll be swinging up and back at the same height again and again and again and again. All right? Let's see if we can understand from the mathematics how to predict these properties so that in high degrees of freedom, when we can't draw these pictures and we don't have these total energy expressions and we don't understand what they mean exactly in the same way, we can still derive the same conclusion. Can we predict the different stability properties of the damped pendulum by using these total energy style arguments? The answer is yes. We showed that the power is non-positive. But the fixed point, even though the power is non-positive, that was enough to show stability in the damped harmonic oscillator, the linear problem. But the fixed point now, it turns out, may or may not be stable. How can we understand that? We took the total energy and we looked at the total energy as a norm in the damped harmonic oscillator. And indeed, for the pendulum, when you look at the total energy expression in the phase plane, you can see that close to the origin, the level curves of total energy indeed are norm-like. They encircle neighborhoods of the origin. In contrast, if you look at the total energy curves up at the fixed point at the top, where you're pointing exactly up and you're at zero velocity, then I think you can see that the total energy is not at all norm-like. The total energy is saddle-like. The total energy is saddle at the top, and it's a norm at the bottom, or norm-like at the bottom. And again, this is a property that nonlinear systems will frequently, almost always have, that linear systems can't have. Either the fixed point is going to be saddle-like, or it's going to be bowl-like. It's going to be norm-like at the bottom. Can we understand why? Can we understand what's going on? Well, we don't have, because this is a non-linear system, we can't get a closed form exact solution to the ODE. And so let's use the simulations, the numerical simulations of a kind that you'll be doing in your exercises and have been. The simulations will help us understand what's going on. The total energy at the bottom of the pendulum looks very much like the total energy of the damped harmonic oscillator. This plot, which is the total energy of the damped pendulum, looks very, very, very much like the corresponding plot I showed you of the damped harmonic oscillator. Only now, instead of position and velocity in the base plane, we've got angle and angular velocity in the base plane. I'm plotting the numerical trajectories along the level curves of the damped harmonic oscillator in its phase plane. And then in blue, I'm plotting these same trajectories along the height function of the total energy when the total energy is close to the fixed point. And you can see that the vector field arrows are pointing down on this total energy basin, and it gives us a basin. So it's almost indistinguishable. It's very, very close and almost indistinguishable from the situation we had with the damped harmonic oscillator. The level curves are enclosing neighborhoods, namely the level curves of the total energy are norm-like in the vicinity of the bottom fixed point. And so I conclude, because the power is non-positive, the total energy is bowl-like and the power is non-positive, and so that tells me, without ever having to draw these pictures or solve the differential equation to get the red flow, which I can't, it tells me, even without this picture, what's going on. It tells me that all the trajectories, no matter where they start, if they start inside this basin, they're going to have to be flowing down to the bottom of the basin. And so we say, we call these initial conditions that flow down to the bottom, we call that the basin of attraction. And very much you're invited to think about this as all the initial conditions that are under the overspreading shoulders of that total energy funnel or total energy basin function. Okay. In contrast, the total energy at the top is not basin-like at all. It gives rise to a saddle. And so when I plot the red trajectories of the phase plane up in the total energy space, where I'm implying them as blue, you can see that even if the power is always decreasing, and so the height is always going down, but I'm trying to come to this stable fixed point. I always slide away from it because of the saddle. The only way that I'm ever going to physically see that fixed point is if I started exactly pointing up, which I'll never be able to do, or if I exactly started on the rim, on the ridge of this saddle. If I started exactly on the ridge, I'd flow exactly down and stop at the top. But there are perturbations in the world, and I will never exactly be able to start on that ridge, and so I will never ever see that orbit whose trajectories lead down to the unstable fixed point. Instead, I'll see all these red trajectories which depart, no matter how close they started to the fixed point, they'll eventually depart from the fixed point. So even though the power is negative, because the total energy at the top is not norm-like, it's not enclosing neighborhoods, the level curves of the total energy run off, away from the fixed point rather than enclose it, I get an unstable fixed point even though the power is negative. And this is a profoundly important point. I get no basin here. There's no basin at all. If I'm lucky, then the solutions will fall their way down to the neighboring, to the basin of the neighboring fixed point, which of course they do in this case. And so this general idea is going to be profoundly important throughout the whole course. And what this begins to help us see is that we need a qualitative theory. For the damped harmonic oscillator, which was a linear time invariant system, I was able to get closed form solutions. Moreover, I was able to get a total energy equation that was an ordinary differential equation in scalar form. Namely, remember what I did. I took the total energy in the right coordinate system. Instead of taking eta in harmonic oscillators, I took eta tilde, which is the harmonic oscillator total energy in the y coordinate system, in the real canonical coordinate system. And in that coordinate system, the total energy looks like a norm squared. I took the power, I did the power computation, and I realized that the power equation gives me a differential equation in eta tilde. A scalar differential equation in eta tilde, which is linear, enables me to completely solve what the total energy is doing. And if sigma is negative, it's clear that the eta tilde has to be going to 0. If eta tilde is going to 0, because it's norm-like, because it's literally a norm, eta tilde couldn't go to 0 unless magnitude y is going to 0. And magnitude y going to 0 means that we're sticking close to the fixed point at the origin. So the fact that the total energy was norm-like was crucially important in making use of the non-positivity of the power formula. It was an explicit norm because I took the right coordinates, and I got a scalar linear time invariant energy ordinary differential equation, and that gave me the stability conclusion that I wanted. In contrast, the damped pendulum shares many of the same features, but crucially, I don't get a scalar ODE in the energy. Let's see. It's a nonlinear time invariant system, so I'm out of luck if I want closed form solutions. I didn't need the closed form solutions in order to get myself a handle on the power. Remember, to get the power, all I need is to take the total energy, which is the kinetic energy plus the potential energy, and take the inner product of the gradient of that total energy with the vector field. When I did that, I get a function which once again is non-positive for positive values of the damping coefficient B. But what I was able to do in the linear case, what I was crucially able to do in the linear case, was I was able to write down a total energy differential equation, a scalar differential equation. The right-hand side of my power formula could be expressed as a function of the total energy itself. Now, my total energy is potential plus kinetic, but my d by dt, my power formula, is not a function at all of anything related to the potential energy. It only depends upon the kinetic energy. And so I'm not going to be able to express the right-hand side as some kind of a function of the total energy. And because I don't get a scalar differential equation in total energy, as I did in the scalar case, it's not entirely clear what to do. Now, this is not the mathematical problem. Mathematically, we're going to be able to show that we get the same conclusions, but there's a little bit more work to do. And starting to do that work is the beginning of what's called Lyapunov theory, and that's what we're going to do to end out this unit and, in fact, to end out the week. So what we want to understand in this qualitative theory is what was the norm-like property, how do we express it, and then how do we get rigorous conclusions out of that norm-like property without a scalar ODE. And that's what we're going to be doing moving ahead. Namely, we're going to be studying linearization. We're going to be observing that locally near a fixed point, we can generally use the Taylor approximation of the nonlinear vector field to get a Taylor approximation of the nonlinear flow. And at the same time, we're going to generalize these notions of total energy. We're going to get what are called Lyapunov functions, which are generalized total energy functions, which, when they're local near a fixed point, have stability properties that can be formally characterized by a generalized notion of total energy. And in the long run, it goes beyond the limits of this course, but it's profoundly important for robotics. The Lyapunov functions actually give rise to a global notion of total energy. There's a global theory of Lyapunov functions, which is a little bit weaker, but still very, very, very important. And it's bound up with what the dynamicists call the fundamental theorem of dynamical systems. And we'll mention this toward the end as a way of showing you that these ideas are quite general and quite profound and strong for robotics. But it goes beyond the scope of this course at this level to really give you much of the mathematics of those ideas.